Okay, no one is still joined, so I'll wait 5 minutes. Then after I'll start the session. Maybe participant will join, then after we'll start. So week 10, today is I'm going to teach week 11, but week 10 I have recorded study, which was scheduled on 30, but due to some reason I have taken on 6, that is study. So already uploaded on YouTube channel. So if anyone want to see, you can go. So I have solved a lot of problems, and also the PDF I have uploaded in the Google Drive link. You can also go through these PDFs. Or if anyone have any doubt, you can ask in the next class, week 12, or I'll take also an extra session on 15. So okay, so I'll wait 5 minutes. After 5 minutes, I'll start. Zilarsan, I'm audible. Please just confirm whether I'm audible or not. Please just confirm whether I'm audible or not. Anyone?
Yes, audible, sir.
Okay, fine. So let us start. So today I'm going to take the week 11. This is so week 11 is about your approximate solution of the Navier-Stokes equation. So we'll discuss about the boundary layer approximation, then the lecture second and lecture third. So based on this, actually I have the problems. So before moving on the problems, I'll just show you some concept regarding your this boundary layer approximation. So what is actually boundary layer approximation? So here you have just seen the two photographs. This is 1 and 2. And this is your Euler equation and this is your Navier-Stokes equation. And yesterday I have discussed your how you will get the from Navier-Stokes equation to Euler equation. So just I'll recapitulate from your previous, that is study class. So this is your, I'm going to write the Navier-Stokes equation for incompressible fluid. So del U in the vector calculus form I'm going to write del V by del T plus V so rho is equal to, this is your pressure term, then your body force, then your dynamic viscous term. So this is your Navier-Stokes equation complete. This is your Navier-Stokes equation. So from Navier-Stokes equation, how you will get your Euler equation? Just neglecting this term. When you will neglect this term, you will get what? Rho del V by del T. Sorry. V del dot V is equal to minus del P vector rho Z. So this is your Euler equation. So as you can see very clearly, there is no viscosity. There is no viscous term in the Euler equation. So if the viscous term in not Euler or in the Euler equation, so viscosity, the dynamic viscosity is directly related to the resistance. Resistance. If there is no resistance, so Euler equation not consider the no slip condition. Whatever we have already discussed, the no slip condition at the boundary level, at the wall, the the fluid velocity is zero. That is no slip condition. But when you will go to solve the fluid problem using the Euler equation, so no slip condition is not valid. No slip condition is not actually account in the your Euler equation. So that's why Euler equation here is written the slip means no your resistance means no dynamic viscosity, and Navier-Stokes equation have the your dynamic your viscosity term. So in Navier-Stokes equation at the boundary level, no slip condition is considered, which is actually happen in the fluid mechanics. So for actual solutions, so we cannot solve the actual problems or physical problem, actually real problem using the Euler equation. So we have to go with the Navier-Stokes equation. We have to go with the Navier-Stokes equation. But Navier-Stokes equation is a non-linear equation. So how we'll solve such type of equation? Whether it is possible to solve. So with this concept, so here just you think on that, the boundary layer approximation bridge the gap between your Euler equation, whatever the disadvantage of the Euler equation, this Navier-Stokes equation bridge the gap. That is consider the Euler equation not consider no slip, but this consider the no slip condition, which is actually relate your physical problems. So this is the concept behind your boundary layer approximation. And boundary layer one thing I want to also discuss with the figure actually. Here you can see. So initially we have only we have only the this one your Euler equation, not the Navier-Stokes equation. So how will solve the problems? So the Prandtl, just you see here, the Prandtl 1875 to 1953 introduced the boundary layer approximation, and this was the breakthrough to understand the fluid problems in the different way. So what the Prandtl defined? He defined the fluid near the wall have some boundary layer, and within the boundary layer we cannot neglect the viscous term. Above the boundary layer we can neglect the your viscous terms. Here we can apply the Euler equation, but here we cannot apply the Euler equation because viscous term is there within the boundary layer. So here is the, and your Prandtl gives the idea about how you will solve this your Navier-Stokes equation within the boundary layer, and above the boundary layer you can apply, because above the boundary layer is velocity is very high. As you know, the Reynolds number is rho v. If I write about your characteristics length divided by mu, it is directly related to your velocity. It is directly related to velocity, Reynolds number. If Reynolds number is very high, means Reynolds number is the ratio of inertia force divided by your viscous force. If Reynolds number is very high, it means inertia force is very high compared to the viscous force. So if the inertia force is very high, so here you can neglect the viscous term. Viscous term means dynamic viscosity term, you can neglect, means you can apply the Euler equation. So this was about the boundary layer approximation. So with this definitions, with this some basic understanding, so just I want to show you how you will calculate the boundary layer thickness. Boundary layer thickness means here whatever I have drawn here. How much this thickness, how it increasing with respect to, if you will move from 0 to this direction, so how you will increase. So boundary layer thickness, momentum thickness, these are the formulas sir has already discussed very well. So just I will show you the some formulas just to see, and then we'll solve the problem. I will not go through the all detail, but I'll upload all the things. If anyone interested, you can go. Okay, so yes, here is the displacement thickness. So how you will calculate displacement thickness, like that. So del star is equal to 0 to infinity, and you just remember the formulas. And displacement thickness for laminar flow, this is your laminar flow. How it related with the x, you can see here. And similarly, your momentum thickness, for momentum thickness you can see the final, I'll show you the final equation. This is your final equation for the momentum thickness, and this is your how it is related with the x means when you will move from here to here in this direction, how this your momentum thickness changes. Okay, so one thing is very important, remember please. So if you have a plate, so initially your boundary layer is laminar, then after as increasing, because your Reynolds number for this plate flow over the plate, Reynolds number will be the rho v and this x direction by mu, dynamic viscosity. So as your x will increase, let us suppose x is 0 here, here is 1, here is 2. As x is increased, Reynolds number will be increased. Reynolds number will be increased for plate. So initially your Reynolds number is less, means your boundary layer is behaving like laminar. Then after transition, and then after fully your turbulent. So transition, and here is turbulent, and here is laminar. So boundary layer behave like that. So remember these things. Okay, so now I will solve the problems. So first question is, if velocity distribution in a laminar boundary layer we are talking about this, within this laminar boundary layer can be assumed. Here you have one equation, y by delta. The ratio of momentum thickness to the normal thickness delta is given by. So here question is, you have to calculate the ratio of momentum thickness divided by your delta, means displacement thickness. So please just try to calculate. No, here is the to the normal thickness delta, not your displacement thickness. This is delta is given. So you have to calculate theta by delta. So please just try to calculate and try to write your answer in the chat box. So, okay. So no one joined still. I think the student had left the class. Okay. So I'll report. So just you can think here the question is about you have to calculate the ratio theta by delta. This topic little bit advanced from your undergraduate level, so you have to understand. So how you will solve? Let me just show you. So momentum thickness is what? As I have told you, as I have just in the previous slide I was showing the formulas for momentum thickness is nothing but 0 to infinity is equal to u by u 1 minus u by u. Let us verify. Yes, momentum thickness is 0 to infinity u by u dy. Here is dy. Now you can put the so 0 to delta. Your boundary layer thickness means 0 to delta u. U by capital U is given already y by delta. Y by delta 1 minus y by delta dy. Now integrate. Y by delta dy minus y square by delta square dy. After your integration you will get y square by 2 0 to delta minus y cube by 3 delta square 0 delta. So here you have to apply your lower limit, upper limit. Lower limit is 0, so there is no meaning. So you will come up with your delta square divided by 2 delta minus delta cube divided by 3 delta square. So delta delta will be cancelled out, and here delta square only one delta will remain. So delta by 2 minus delta by 3. So this will be your 3 delta minus 2 delta divided by 6. So 1 by 6. 1 delta by 6. So theta is your 1 delta by 6. So you need to calculate this theta by delta. So 1 by 6 delta divided by delta. So final answer is 1 by 6. So option C will be correct. Remember please, here option C will be correct. Okay, let us move with the next question. So solution is given here. You can also follow whatever I have discussed. Next question. In a boundary layer development, in a boundary layer developed along the flow, in a boundary layer developed along the flow, the pressure decreases along the downstream direction. the pressure decreases along the downstream direction, the boundary layer thickness would be tend to decrease along the flow, remain constant, increase rapidly along the flow, increase gradually along the flow. So this is a four option. So just think on that, how, what is the meaning. So as I have told you, the relation between your x direction and your boundary layer thickness. So how you will think on that? Very important. Okay. So again, I'll go here. So as you can see, your thickness, boundary layer thickness is increasing. Here you can also think on that. The boundary layer thickness is increasing with respect to the x. Also, it is directly proportional to. This is your boundary layer thickness. Okay. So it is directly proportional. So you can correct or increase with the x. Increase gradually along the flow. So option D will be correct here. This option D will be correct. In a boundary layer development along the flow, your pressure, the pressure decrease along the downstream direction, the boundary layer thickness would be increase gradually to the flow. Here is the explanation. In boundary layer theory, the thickness of boundary layer delta always increases with distance downstream because of the viscous diffusion of momentum. Viscous diffusion of momentum. So you can expect question based on this term only. If the pressure decreases in flow direction, it is called favorable pressure gradient. This helps stabilize the boundary layer and delay separation if your pressure is decreasing. Third one, under such conditions, the boundary layer thickness still increase, but it does not, it does so gradually rather than rapidly. Remember please. It does so gradually rather than rapidly if you have the condition of pressure decreases along the flow direction, then gradually along the flow. Remember please. Here increase rapidly along the flow. Here is increase gradually along the flow. It will be gradually along the flow because pressure is decreasing. So next question, very very important, numerical type. The mean drag coefficient CDF for a laminar boundary layer over a flat plate found is 0.05. You have this value. CDF is 0.015. Okay. If all other flow factors remain the same and the length of the plate is decreased to, if initial length was L, then in the second case it is L by 4, its original value, the drag coefficient CDF should be. So just think on that. So how your drag coefficient related with the length of the plate. So if you know these things, then very easily you can calculate, otherwise it will be the very difficult. Still no one join. Okay, Very important question. So little bit boundary layer approximation or boundary layer theory is little bit advanced compared to the other topics in the fluid mechanics like your pipe flow and laminar flow, your concept based on the Bernoulli's equations and all, little bit advanced, your boundary layer approximation. So you have very patience to read the this actually particular topic. Even your dimensional analysis not much your tough compared to this boundary layer equations. You have to patience about it. Okay, so let me just show you because no one joined, so let us discuss the answer. So here is your CF. Here you have change in mean drag coefficient when the plate length is reduced to 1 by 4. This is the question statement. Now, for a laminar flat plate boundary layer, the mean skin friction coefficient scale as like that. Your skin friction is, or drag you can say, it is directly proportional to, inversely proportional to 1 by root REL. And your RE is directly proportional to L. Means you can write here 1 by root L. Means CDF 1 is equal to 1 by root L1. CDF 2 divided by 1 by root L2. So now you have these two things. L1 you have L and L2 you have L by 4. So you can write here. CDF is given already. How much? 0.015. Okay. So just take the ratio 0. Let me just write very clear. CDF 1 divided by CDF 2 is equal to 1 by root L1 divided by 1 by root L2. So ratio will like that, L2 by L1. So your L2 is L by 4 and this is your L. So root L will be cancelled out. So you have in your hand root 1 by 4 means 1 by 2 and CDF 1 by CDF 2 is equal to 1 by 2. So your CDF 2 is equal to nothing but 2 into CDF1. So 2 into 0.015, so we will get the final answer 030. So this is the how you will solve. So this is your final answer. A option is correct. 0.03. Here you can also see your local drag coefficient. From this concept also you can solve the similar thing whatever we have here discussed above, the similar thing here. Your CF is directly proportional to REX and RE is directly proportional to your X or L you can say. Okay, in laminar and turbulent, just think on that. If the flow is turbulent, it is directly proportional to 1 by 5, please, not 1 by 2, not root 2. It is 1 by 5, remember. Okay, next question is, a flat plate with a sharp leading edge is placed along a free stream of fluid flow. The local Reynolds number is 3 centimeter from the leading edge is 105. The local Reynolds number at 3 centimeter from the leading edge is 105, or I think it is 10 to the power 5. Okay, so what is the thickness of the boundary layer? So question is here, the thickness of boundary layer. So how it is related? Thickness of the boundary layer. Okay, okay, still no one join. Okay, anyway, I am recording the video, no problem. So question is, a flat plate with a sharp leading edge is placed along the free stream fluid flow like that. If his free stream water is flowing, a plate is putting there. You have put a plate, sharp is. You have put it here a plate like that. And water is flowing over it. So now Reynolds number at 3 centimeter from here to, let us suppose, 3 centimeter is 105, or I think it is 105 or 10 to the power 5. Let me just see, after calculation we can get what is the thickness of the boundary layer. So it is, how it is related, is your boundary layer thickness. You have three variable: boundary layer thickness, x value, and Reynolds number. And another you have term of whether this flow is laminar or turbulent, because for laminar the relation will be different and for turbulent relation will be different. So how you will identify whether flow is laminar or turbulent? So this is another thing here. The flow type, we have to know. Reynolds number in such case is what? Rho V x divided by dynamic viscosity, but here you don't no need to calculate because already given. So 105, or I think it's 10 to the power 5 because it is plate case. So 10 to the power 5 it is coming in the laminar, 10 to the power 5. So laminar flow, for laminar flow the relation is, you can just see here, the relation. So now just calculate the your answer. So delta is, you have to calculate delta. X value is given 3 centimeter. Okay, now your 5 divided by root under your Reynolds number. Reynolds number, let me just see. Yes, 10 to the power 5 is given. This is 10 to the power 5. So now you can calculate very easily. Let me calculate very precisely with calculator. Okay. So 10 to the power 5 square root, sorry, 10 to the power 5 is equal to, then take a square root. Okay. This will come 31622. Then your delta is, and this will be your 0.03. So 5 into 0.03 divided by 316.22. So it is around 0.00047 meter, because everything we have, because your this centimeter I have put it in meters. So here the thickness of the boundary layer, I think, in mm. So when the question is not mentioned, so you need to calculate in mm. So in mm you can very easily calculate after multiplying with the 1000. So you will get delta is 0.47 mm. So this will be your final answer. That is option number B is correct for this. Okay, so now move with the next question. So here formula is given, as you can see. This table I have taken from your Sinjal Simbala book. The summary of expression for laminar turbulent boundary layer on a smooth flat plate lying parallel to uniform stream. So these are the conditions: a smooth flat plate and lying parallel to the uniform stream. Anyone join? Let me just check. Oh, still no one joined. Charge is full. Okay, so let me just go through the. So here you can see the star representing laminar values are exact are exact and are listed to 3 significant digits, but turbulent values are listed to only 2 significant digits due to the large uncertainty affiliated with the turbulent flow field. So here you have to remember one thing: in the laminar, 2 significant digit, here you can see 4.9172 1. Okay, but in the turbulent values are listed only 2 significant digit, but in case of turbulent the 2 significant digit is considered. And your the things, this sign you're related to your orbitant from 1/1/7 power law for turbulent flow, and this column is calculated based on orbitant from 1/7 power law combined with empirical data for turbulent flow through smooth pipes. Just think on that. So here you can just see with the combination of the empirical equations, here you can see the difference. Here is 1/7, here 1/5, 1/7. So in turbulent flow, depend on whether you are calculating with 1 by 7th power law. If you are calculating with the 1 by 7th power law, initially we are discussing about the CF in the previous question. So if you are calculating with the 7th power law, it is 1 by 7. Otherwise, the second condition obtained from the 7th power law combined with the empirical data, you will come up with the 1 by 5. So you just care about it in the questions. Okay, so your boundary layer thickness is related like that, and your displacement thickness is, just see the laminar one, and momentum thickness is this, and your local skin friction coefficient is like that. And in case of turbulent, you can just see everywhere power 1 by 7th 1 by 7, and in second case power 1 by 5, but the digit here, it changes, significant changes. Just think on it. Okay, so now let us move with the question. So this was the just concept, remember always these formula you have to remember, these four formulas, this four formula you have to remember in the question. Maybe in the gate exam or other exam, direct question may be expect you can based on this. Okay, what is the ratio of displacement thickness to momentum thickness? Here we need to calculate the ratio of displacement thickness to momentum thickness for linear velocity distribution in laminar boundary layer along the flat plate. So what is linear velocity distribution? So this is again concept. So linear velocity distribution means this. Actually, your velocity distribution is parabolic in laminar, like that. Let me just show you very clearly in case of boundary layer. So up to here, this is laminar boundary layer. After that, the constant flow. If this is depth, constant flow. Up to here, it is parabolic in, this is your laminar. Up to here, let us assume the laminar boundary layer, then transition, then your turbulent. So parabolic, then after constant, means whatever the value will be here, the same value everywhere, but here is changing, here is other value, here is other value, means you are putting u is in this direction and y is in that direction. So here you will be different, here you will be the different, here you will be the different, so like that. So question is asking about the displacement thickness, it is your del star divided by momentum thickness ratio you need to calculate, and this is your parabolic, but question is talking about the linear velocity distribution. So what is linear velocity distribution? Your small u divided by, this is your capital U, this is your small u. You can just expect anywhere you can take the small u. This value is small u, you can say. So your small u capital U is linear relation, means what? Y divided by delta. Remember. So you have this linear relationship, and after calculating using the formula, you can very easily calculate your ratio of displacement thickness to momentum thickness. Very easy question. So let me just see, and you can join. Okay, one join. Very easy question. Anyway, I will explain very clearly. So what is your displacement thickness? The formula of displacement thickness is nothing but 0 to infinity 1 minus small u by capital U dy. What is the formula of your theta, momentum thickness? As we have discussed, 1 minus, you can put the value of y by delta in both. So let us first solve this. 0 to delta 1 minus y by delta dy. So integration minus y by delta so here is delta, here is y not delta, minus y square by delta 0 to delta means delta minus delta square by delta square by 2 when we will do integration. So here cancel out. So delta minus delta by 2. So you will remain delta by 2. Now displace your momentum thickness theta. So theta will be 0 to delta u, that is y by delta, minus 1 minus y by delta dy. 0 to delta y by delta, just simply calculation, not much, delta dy minus 0 to delta your y square divided by delta square dy. So y square by 2 delta 0 to delta minus y cube by 3 delta square 0 to delta. So we will come up with delta square by 2 delta minus delta cube by 3 delta square means delta by 2 minus delta by 3. So final expression will you will get delta by 6. Now you have to calculate the ratio. So ratio will be delta by 2 divided by delta by 6. So delta by 2 into 6 delta. So delta will be cancelled out, 2 3 is 6. So final expression will be your 3. D option will be correct. So this is the way of solving such type of question. Very easy question, not very hard. Okay. So next question is, in turbulent boundary layer. Here the question is turbulent boundary layer. Not we are talking about the laminar one. Turbulent boundary layer on a flat plate. The velocity distribution is given by 1 by 7th power law. Remember, 1 by 7th power law. if the boundary layer over the whole plate, if the boundary layer over the whole plate is turbulent, the ratio of shear stress tau 1 and tau 2 at two sections at distance from leading edge x2 is equal to 5x1 is given by. So you have to calculate the ratio tau 1 divided by tau 2, and tau 1 will be your at let us suppose x1, and tau 2 will be your x2. So you have to calculate. So first here the condition is given. First condition is turbulent boundary layer, and the boundary layer here one thing is also given. Boundary layer over the whole plate is turbulent. Okay. And another condition is you have to calculate with 1 by 7th power law. Whatever you will apply the formula, this should be based on your 1 by 7th power law. Another things, the condition is given. Your x2 is 5x1. So if your x1 is x, then your x2 is 5x. So this is the condition is given. Now you have to understand one thing. In turbulent boundary layer case, these all three conditions keep in mind, and you have the relation between tau and your distance x. So what will be the relation in based on the 1 by 7th power law? So we have discussed or not earlier. Here we can see, okay, here there is not any term which is your related to shear stress. Okay, I think in the concept part I have. Okay, this is your turbulent boundary layer concepts here. I don't know whether they have considered or not. Okay, anyway, I have the solutions, but just I am looking whether your shear stress relation is given or not in the PPT. Okay, some problem is given based on your shear stress, but the final I am looking for the final equation. I think not given. Okay, not worry. So let us move with the final answer. So what will be the formula? Just I'll show you. Yes, question number 6. So formula will be 1 by 7th power law, you know already. So it is correct or not? One in 1 by 7th power law, it is related with the your 1 by 5. I think not. CF is related with your, okay, with X. It is 1 by 5, not Reynolds number. Here Reynolds number is given, but Reynolds number is also your Reynolds number is your rho Vx divided by mu. So Reynolds number is directly proportional to x. But here in the solution part, it is given x to the power 1 by 5. Whether it is correct or not. Okay. So we can do one thing. If it is 1 by 7th power law, so 1 by 7th power law means this. Your velocity with your free stream velocity. This is free stream velocity. Free stream velocity means uh, the velocity which is your equal to the, let me just show you the pictorial representation, then you can very easily understand. If let us suppose this is your boundary layer, so up to here your velocity is varying, but after that your velocity is constant. Means whatever the velocity is here, the similar velocity will be the here. Means this is your free stream velocity. You can also say this is your free stream velocity, which is u infinite, you can say infinite, and this is your u 99%, 99% of your u infinity. So these things. Okay, so for turbulent plate, 1 by 7th power law is this, and the local skin friction coefficient is like that. And why we are comparing with the local skin friction, you know already, because of it is related with your uh, shear stress. Here you can see the formula. Related shear stress to the skin friction coefficient, and the ratio of your, so your tau is directly relation with the CF. So means tau 1 divided by tau 2 is equal to CF1 CF2. CF1 divided by CF2. Now you can write very easily. And your CF, here it is given for empirical relation 1 by 7th power law, CF is like that. But here it is not given in the table on the Signal Simbala book. 1 by 7th power, you can use this one also. No issue, I think. So calculation will not impact. Maybe a little bit value will differ because 1 by 7 and 1 by 5 power may be different. And your CF is related with 1 by r to the power 1 by 5 1 by 7 means CF is equal to 1 by x to the power 7 means CF1 x1. So here tau 1 is equal to 1 by x1 power 1 by 7. Tau 2 is equal to 1 by x2 power 1 by 7 means, so x1 value is x, and when you will write the ratio tau 1 divided by tau 2, you will get x2 1 by 7 divided by x1 1 by 7 means x2 is, what will be the x2 value? X2 is nothing but 5x, and this is your x. So 1 by 7 1 by 7. So here you have 5 to the power 1 by 7. So 5 to the power 1 by 7, what will be the values? So 5 to the power 1 divided by 7, 1.25. So it is coming 1.25. 26 you can write, 1.258 is coming, so 1.26 you can write. So just match 1.258. So you can go with the option A. Here option A is correct. Or your 1.379 is coming when you will consider this one obtained from the seventh power law combined with the empirical data for turbulent flow through smooth pipes, when we will combine these things. But we are discussing about, the question is clearly telling 1 by 7th power law, so we'll go with this. So you can say this calculation is not correct because this is not based on your 1 by 7th power law. Here is again I have put it your table, the summary table. This table is very important. So one thing you can say very clearly here, the note point, in your laminar flow or turbulent flow, your tau is 1 by root x, or you can say 1 by 2, and here tau is directly proportional to 1 by, inversely proportional to 1 by 5 or 1 by x to the power 1 by 7. Depend on the how the question is telling. So remember always, you can expect question from here. Most probably this, from this the laminar flow conditions, most probably question I have seen in the many competitive examinations. So now the question number 7. Just see anyone join? No. Okay, so I'll take here 5-minute break, then after I'll come again for solving the session, for solving the question number 7. Okay, so now let us start again. Question number 7. So question 7 is, what is the boundary layer thickness in centimeter? You have to calculate in centimeter. When a flat when a flat plate of 15 centimeter wide and 45 centimeter long, placed longitudinally in a stream of oil having relative density 0.925 and kinematic viscosity 9 stop, flowing flowing with a free stream velocity 6 meter per second. Okay, so little bit advanced question. So how you will approach? Yes, recording is going on very well. So what will the boundary layer thickness? So here question, you have to calculate the boundary layer thickness. Another things in centimeter, remember. When the flat plate of 15 centimeter wide, you have a plate, you have plate like this. 15 centimeter wide, the width of the plate is 15 centimeters. Okay, plate will be like that. This is your plate. Okay, now hope you will understand. This is your plate. So this width is 15 centimeter. Or here I am writing on the bottom 15 centimeter and 45 centimeter long. Okay, place longitudinally. If water is flowing like that, means longitudinally in the flow direction. Plate is placed of oil having the relative density oil. So relative density here is given, means the specific gravity of the oil is given your 0.925. So specific gravity, your density will be multiplied with 1000. So 925 kg per meter cube. Relative density means what? The density of oil with respect to the standard one. Standard one is your water. So, and this is specific gravity, relative specific gravity you can say, relative specific gravity. So it is given 0.925 raw oil divided by raw water. So raw water you know already 1000. So when you multiply, you will get raw oil. So that's it. kg per meter cube. Okay, now the kinematic viscosity you have, dynamic viscosity divided by rho, you have 0.9 Stokes. Flowing with free stream velocity, you have velocity also. Six meter per second. So with all data, initially for calculating the boundary layer thickness, you have the two case, whether your boundary layer, or three case, whether your boundary layer in laminar, transition or turbulent. Based on that, you have the formulas. If your flow is laminar, then you have the another formulas. In transition case, we have another formula. In turbulent case, we have another formulas. So first you need to calculate whether your flow is turbulent or laminar or in transition. So how you will calculate? So Reynolds number in case of your flat plate is density divided by dynamic viscosity or velocity into your x divided by your dynamic viscosity. So this is your Reynolds number in case of flat plate, and it is laminar when your the value will be less than or equal to 1 into 10 to the power 5. This is the case of laminar. If it is less than equal to, then it will be the laminar. Otherwise, turbulent. Okay, so how you will calculate? So you know already mu by rho is your kinematic viscosity, so you can very easily put it here. Your Reynolds number will be the velocity into x divided by mu or nu. That is your kinematic viscosity. Let me write very clearly. So this value is, your velocity is in meter. So let us write in the centimeter, because you have value in the centimeter. So 6 meter per second means the 60. Six hundred centimeter per second. So what will be the value of x? So let us, I am going to calculate at here. The value is not given. Actually, in the questions should mention at what location we need to calculate your this thickness, boundary layer thickness. So let us assume here we are going to calculate at 45 centimeter here at the end. So 45 centimeter divided by your Stokes 0.9. So this is also your CGS unit, centimeter unit. So now you can calculate. Your RE will be, let me just calculate, 600 into 45 divided by 0.9, 30,000 means 30,000. So 30,000 means 3 into 10 to the power 4. Yes, it is in the case of laminar. So you can apply formula laminar one for boundary layer thickness, this. So delta divided by x is equal to 4.91. Sometimes you can put the 5 also, then Reynolds number. So your delta divided by 45 is equal to 4.91 divided by 30,000. So delta is equal to 4.91 into 45 divided by, if my calculation is correct, you will get the exact answer. So I will take the square root. So 137, this will give you 173.2, and your 4.91 into 45, this will give you 220 divided by 173.2, 1.27. So this is your 220.95. So finally after calculation you will get 1.275, so approximately 1.3. So option A will be correct here. If my calculation is correct, you go with the option A. Let me just see. Yes. So 1.3. Your Reynolds number is 3 into 10 to the power 4, whatever we have calculated. This is your, and now you very easily you can calculate. Okay, I have considered 4.91, that's why I am getting 1.27. If you will put the 5 exactly, you will get 1.3. Okay, so now we have solved a lot of numericals. Now a little bit very easy questions which are theoretical type. So the first question is, who introduced the boundary layer theories? So in the beginning of the class I have told already, the Lewis, the Prandtl theories. The Prandtl introduced the boundary layer theories. So remember, option A will be correct here. Next one, yes, here you can see the Prandtl introduced boundary layer theory is in 1904. And explaining the viscous effect near solid surface. Viscous effect near solid surface means what? Means near the your boundary, near the your wall or boundary layer will be the form, and within the boundary layer, that is the near the surface, your viscous effect is very dominated, and above the boundary layer viscous effect is you can neglect also, not dominated much compared to the near the wall. So this was the concept. Next one, boundary layer is defined as the region where the viscous effect are negligible, the region of irrotational flow. Option C, thin region near the surface where viscous force are significant. Next one, region of constant velocity. So boundary layer is defined as I have discussed lot of questions, lot of discussion. So hope you will understand. The thin region near the surface where the viscous force is dominated or significant dominated. So option C will be correct here. The boundary layer is thin layer close to the solid boundary where the viscosity influence and velocity distribution. Yes, viscosity influence affect your velocity distribution means near the wall. Again, I will draw. So here is no slip condition means velocity is zero. If the velocity is zero, the effect of this zero will try to, if here is zero velocity, then just above the velocity will be little bit higher than zero, but the layer at zero level will try to reduce the velocity of this and reduce the velocity at this point. Similarly, this point is try to reduce the velocity of this point, this try to reduce the velocity at this point. So here the velocity is zero, here it little bit higher, here little bit higher, here little bit higher, here little bit higher, and after some distance your velocity will be the constant. So remember please. So this is the concept. Due to your viscosity, your velocity distribution influence. Velocity distribution influence means here is velocity is little bit lower, then little bit higher as you will move from away from your wall. So this is very important concept. Okay, now let us move on the next question. Here again, whatever we have discussed, the same thing. For a flat plate, the boundary layer thickness in laminar flow varies as. Just think on that. Option A is given. Delta by delta is directly proportional to 1 by 2. Delta is directly proportional to 1 by 3. Delta is directly proportional to x. Delta is directly proportional to x square. So which option will be correct? For a flat plate, the boundary layer thickness in laminar flow. The question is talking about laminar flow. So as you know, though, in the laminar flow, your boundary layer is x is equal to 5 divided by root RE, and root RE is nothing but rho velocity x divided by dynamic viscosity. So question is asking about only the s, your x. So delta by x is equal to, everything is constant, so I will write here one constant and root x. So now you can think. So delta by x. So when we will cancel out, x means what? X means root x. X to the power root means what? X to the power 1 by 2. So when you will 1 by 2 power, 1 by 2 power, again it will come x. C by root x. So 1 root x cancel out. So your delta is constant root x. So it is, you can write very clearly, it is directly proportional to x to the power. Some student may be confused with this concept. Delta is equal to 5x divided by root x divided by rex. some student may be confused because you cannot consider, if anyone not consider this Reynolds number x whatever is in the Reynolds number, so you cannot clearly write the relation between your delta and x. So you have to remember, someone can write the delta is directly proportional to x with this expression directly without checking your RE. So you should avoid such type of problems, such type of situations, or such type of your thinking also. Okay, next question is the displacement thickness represent. Very important question. The displacement thickness represent extra distance the boundary move outward, reduction in momentum due to viscous drag, equivalent thickness replacing real velocity profile by uniform flow, equivalent thickness replacing real velocity profile by uniform flow, wall shear stress. You have four options. So displacement thickness represent what? The content related to this displacement thickness and all I have provided. I'll just show you. Initially I have provided, but I have not discussed the concept today. I have just discussed the today is the boundary layer approximation concept, not your this displacement thickness and the momentum thickness concept. I have not discussed, just I have shown you the formulas. Yes, here you can see displacement thickness is the imaginary increase in the thickness of wall as seen by the outer flow due to the effect of growing boundary layer. So displacement thickness is the imaginary increase in the thickness of wall as seen by the outer flow due to the effect of growing boundary layer. So when you will go through this, okay, here I'll just show you. The displacement thickness is the distance. The displacement thickness is the distance that streamline just outside the boundary layer. Streamline just outside the boundary layer. For this, for here, the streamline just boundary here. For here, this is third one. For here, this one. Just outside the boundary layer. Okay. Is deflected away from the wall due to the effect of boundary layer. So displacement thickness is related with the streamline. Remember, here two thing is coming. Displacement thickness is related with the streamline. Which streamline? Which is just above, just outside your boundary layer. Yeah, just see here. Is deflected away from the wall. Is deflected away from the wall. Okay, here you can see the distance at this level is this much, but here is the distance is this much. Means as you are moving from the downstream, as your boundary layer is increasing, means your streamline also increasing. Streamline, the distance from wall, the distance between wall to streamline also increasing. So this is the meaning. away from the wall due to the effect of boundary layer. And why this is due to the boundary layer formation? Means here you can see very clearly the streamline is your at the beginning of your streamline, at beginning of your plate. Here you can see your streamline is this dotted streamline. You, as you can see, this is the your exact streamline dotted without deflection. But due to the your boundary layer formations, this is streamline little bit away from this. So the distance between this dot two line known as your displacement thickness. So displacement thickness is what? Displacement thickness is nothing but whatever the displacement of your streamline. Just think on that. Whatever the displacement of your streamline, that's displacement is known as your displacement thickness. And streamline you have to consider just above the boundary layer, not anymore. So this is the concept. So now you can very easily solve that particular question. So you have to very patience. You have to have very patience for the boundary layer approximation topic. And try to understand by yourself also. You can read the book also for more clarification. Okay. So let me just move. Yes. Displacement thickness. So displacement thickness option, let us read the again option. The extra distance of boundary move upward. Extra distance, the boundary move outward. No, the reduction in the momentum due to viscous drag. Equivalent thickness replacing real velocity profile by uniform flow and the wall shear stress. Which option will be correct? So your option will be equivalent thickness, the replacing real velocity profile by uniform flow. So displacement thickness account the mass flux deficit caused by slower velocity in the boundary layer. Means just try to understand. I'll just give you idea. As we have seen these things, your boundary layer will form like that. Okay. So the velocity here, let us suppose water is flowing in this direction like that, and velocity at surface here is your 5 meter per second. So let us just draw the velocity profile. After this boundary layer, your velocity profile will be constant. That is, here your velocity will be 0. Here your velocity will be little bit less. Here little bit less. Here little bit less. But from here your velocity will be the 5. Here is your 5 meter per second. Okay. Now let us move little bit downward. up to here, up to here, your velocity is, from here, your velocity is 5 up to that. But within this, your velocity is less than 5. So as we can think on that, here you can just think. Here, from the the velocity here is 5, here is 5, means up to that much depth, up to that much depth, your velocity is 5. Here, velocity 5 means your maximum velocity. Maximum velocity is, the depth of the maximum velocity is here is more. The depth of the maximum velocity here is little bit less. Similarly, depth of the maximum velocity little bit less. Depth of the maximum velocity little bit less as you will move in the downstream. So if the depth of the velocity will be the less, depth of the maximum velocity means whatever the mass flow rate, whatever the mass flow rate flow from here, if I consider section 1, section 2, section 3, whatever the mass flow will from here at section 1, the similar mass should be flow m1, m2, m3, it should be equal. It should be equal as per your continuity equation. But as you can see, if I write the area of low velocity, area of high velocity, area means the width of your this system, width of the system is constant, so area is depend on your height only, because width is constant everywhere. So area of high velocity, area of low velocity, area of high velocity at 1, area of high velocity at 1 is greater than area of high velocity at 2, greater than area of high velocity at 3. Means here the mass will flow, means if I divide the mass in two parts, mass in low velocity, mass in high velocity. So mass flow rate in high velocity will be more, mass flow rate in the high velocity will be in 1, 2, and mass flow rate in high velocity in 3 will be more. So means as you are moving in the downstream, your mass flow rate in the high velocity zone is reducing. So to maintain the conservation of your fluid flow, conservation of mass, you can say, to maintain the conservation of mass, your streamline little bit deflected. Your streamline little bit deflected as you are moving in the downward direction. Means your streamline will be like that. If I draw here, this is your streamline little bit deflected. Streamline deflected means what? Whatever the fluid is flowing here in the that much area, the similar fluid, that much fluid should be flow in that much area in this region, because of here is your velocity is less, here low velocity zone, your area low velocity zone is much, the area of low velocity zone is much compared to here. So if your water is flowing very slow up to that much distance, means what? You have to have some what? You have to have some extra area. You have to have some extra area for water flow. So as you will move above, your streamline will be deflected like that, because you need more area. So as you will move just above the boundary layer, it will be deflected like that. But originally your it should be like that. Whatever the dotted line was showing, the straight it should be. So whatever the deflection is straight like that, whatever the deflection will be here, so that deflection is known as your displacement thickness, and that is here is rated. Displacement thickness accounts for mass flux deficit cause of the slower velocity in the boundary layer. So hope you will all get. So now let us move in the next question. In boundary layer approximation, which term is neglected? In boundary layer approximation, which term is neglected? Pressure gradient in x direction, viscous term in y direction, inertial term in y direction, pressure gradient in y direction. So in boundary layer approximation, which term is neglected? Just think on that. Y direction, x direction means longitudinally, the flow longitudinally is your x direction and vertically is your y direction. So now just think, in the boundary layer approximation, which term is neglected? Pressure gradient in x direction, pressure gradient in y direction means del p by del y. This is this, and this is pressure gradient in x direction, and viscous term in y direction, and inertial term in y direction. So this is your pressure gradient in the y direction will neglect. In the boundary layer approximation, pressure variation across the thin boundary layer in the y direction is negligible. We discuss your pressure gradient, how change with respect to x as you are moving from here to here. What will be the value of pressure gradient here? What will be the value of pressure gradient here? But in the boundary layer, within the boundary layer, we not consider what will be the pressure gradient here, what will be the pressure gradient here. We not, just we neglect. If this is 1 2 3, we not consider these things. Pressure gradient del y is 1, the pressure gradient del y at 2, we not, uh, this approximation we neglect. This is the meaning. Next, question number 6. So what is the Reynolds number for transition from laminar to turbulent boundary layer of the flat plate? So very easy question, just the data type question. Just think what will be the Reynolds number for transition from laminar to boundary layer. If I show you the pictorial representation, this is your flat plate, and here is the laminar boundary layer, then transition, then your turbulent. So this is laminar, transition, and this is your turbulent boundary. And how you will calculate? RE, rho Vx divided by dynamic viscosity. So as your RE increasing, you will change from laminar to transition and turbulent. So what will be the value of changing point? So it will be your 5 into 10 to the power 5. Remember, option B will be correct for question number 6. Next question, question number 7. The momentum thickness represent. For this question also, I'll go back in your conceptual part. So let us read first the option: reduction in displacement due to the viscous effect, reduction in momentum flux compared to ideal flow, wall shear stress, and the pressure drag. So before comment on this question, let us move on the concept. Okay, this is your displacement thickness. Now momentum thickness. What is momentum thickness? Here it is given. Momentum thickness is defined as the loss of momentum flux. Momentum thickness is defined as the loss of momentum flux per unit width divided by rho u square due to the presence of growing boundary layer. Means loss of momentum flux. Loss of momentum flux per unit width divided by rho u square. This will be the momentum thickness due to the presence of growing boundary layer. So here you can see very clearly, this is your, this represent your x, that is your displacement thickness, this represent your theta x. For laminar flat plate boundary layer, the displacement thickness is, the displacement thickness, remember, the displacement thickness theta star is 35% of the delta, and momentum thickness is 13.5% of the delta. This is your delta, this is your delta, this is your delta square from here to here, and this is your theta. So remember, means loss, momentum thickness is defined as the, momentum thickness is nothing but is the ratio of loss in momentum flux per unit width divided by rho u square. Rho u square is free stream velocity into density. So this is just your ratio. So here very clearly, once you will go with this proper understanding, you will get. Another measure of the boundary layer thickness is momentum thickness, commonly given by the symbol theta. Momentum thickness is best explained by analyzing the control volume in figure 109. Here is, you can see, for a flat plate boundary layer, since the bottom of the control volume is plate itself, so no mass or momentum can cross the surface, because this is plate, no mass can cross. The top of the control volume is taken as the streamline of the outer flow, and since no flow across the streamline, there can be no mass momentum flux across the upper surface of the control volume. Okay, when we apply the conservation of mass to this control volume, we find that the mass flow entering in the control volume from the left, x is equal to 0, must equal to the mass flow rate. Once we will apply the everything, so I'll not read line by line. So this is the concept here is the loss of momentum flux per unit width divided by rho u square. So now let us move on the question. Okay, so we have solved very clearly. Yes. Yes. Momentum thickness is what? Reduction in the momentum flux compared to the ideal flow. So option D is correct. The momentum thickness is defined as the thickness representing momentum deficit due to velocity gradient. Remember please. Next question. Which equation governs the laminar boundary layer over flat plate? Whether Navier-Stokes equation, Euler equation, Blassius equation or the Bernoulli's equation. Which equation governs the laminar boundary layer over flat plates? This is your laminar boundary layer. So which equation? Whether laminar, Euler, Blassius, Bernoulli's. So remember one thing, the Blassius equation is governs in the laminar. So the Blassius solution is the similarity solutions of Navier-Stokes equation for laminar flat plate boundary layers. Next question. For turbulent boundary layer, the thickness varies approximately as. Here is approximately is given. So you can just think on that. Whether option A will be correct, option B, C, D, which will be the correct. So here is question is approximately. So you can go with 1 by 7th power law or the combination of these two things. So with respect to X, that is talking about. So turbulent boundary layer, the thickness varies approximately. So delta, as you know the formula, delta by X is equal to 0.37 divided by RE X power 1 by 5. So you know one thing, delta by X is equal to 0.37 and your RE is nothing but directly proportional to X. So it is X to the power 1 by 5. So here this is constant. So delta is equal to nothing but x divided by x to the power 1 by 5 means x 1 minus 1 by 5 is equal to what? 5 minus 1. This is x is equal to 4 by 5. So your delta is nothing but this is your constant here. So directly proportional to x to the power 4 by 5. So this will be your final answer. So remember please. Now this is your last question for today class. Skin friction drag on a flat plate is mainly due to pressure variation, viscous shear stress, wake formation or the flow separation. The question is asking about skin friction. Skin friction drag, that is your CFX, whatever we are discussing previously. So it is mainly due to your pressure difference, viscous shear stress, wake formation or flow separation. So obviously it is your based on your viscous shear stress. On a smooth flat plate aligned with flow, the drag is due to the viscous shear stress only. So hopefully everyone, if anyone have any doubt after seeing this video, after my uploading, so you can ask in the next class or in the summary class also you can ask, which I'll take on 15 and your next class is scheduled on 14 and 15, remember please. Okay, fine. So thank you for today class.